So when we have a solution of sodium carbonate, we first think, what's in my beaker? Well, sodium carbonate is a salt. And when I put a salt in an aqueous solution, what happens is it breaks down and it gives me 2 sodium ions and a carbonate ion. I have 0.15 molar sodium carbonate, so I have 0.15 molar carbonate ion. What effect does a sodium ion have on the pH of my solution? None. So, since it has no effect, we do not put that in our equilibrium expression. So now we think, what's going on in my beaker? Well, I have the carbonate ion that is going to react with water to make hydrogen carbonate plus hydroxide. And I have the hydrogen carbonate that's going to react with water to make carbonic acid and a little more hydroxide. Now, we've already looked at these and said that the KB1 is much bigger than KB2. So does this second equilibrium have anything to do with the pH? So we can ignore it because we're not interested in the carbonic acid concentration. We just want to know the pH. So now we can set up our concentration table. So this equilibrium only, the first ionization only, controls the pH. So we have carbonate reacting with water to make hydrogen carbonate ion plus hydroxide. So we have 0.15 molar. We ignore the water. We have 0 and 0. Minus X, X, and X. At equilibrium, 0.15 minus X, X, and X. Now, we say, what can I do to simplify this? Well, my KB1 is 2.1 times 10 to the negative 4th. That's kind of marginal to ignore X, but I'm going to, because I don't want to do a quadratic. Okay? We could do a quadratic, but we're not going to right now. So we know then that KB1 is equal to HCO3 minus times hydroxide divided by the carbonate concentration. So I plug in my numbers. 2.1 times 10 to the negative 4th, my KB1, is equal to X times X divided by 0.15 molar. So 2.1 times 10 to the negative 4th times 0.15 is equal to X squared is equal to 3.15 times 10 to the negative 5th. X is representing hydroxide concentration, and that is equal to 5.6 times 10 to the negative 3rd molar. So now that negative 4th was a little iffy for me deciding could I ignore X or not. So let's just do a quick and dirty check. My original concentration was 0.15 molar. And my X is 5.6 times 10 to the negative 3rd molar, minus 0.0056. So when I subtract, 10 minus 6 is 4, 9 minus 5 is 4, 4, 1. Is that close to 0.15? At this point, I probably would have rounded down to 0.14, but it's all the digits we're sure of and one with some uncertainty, so I'm rolling with it. Okay, we're not going to solve a quadratic here because of sig figs. Because remember, my goal here is teaching you how to do this. And you already learned how to solve a quadratic. We're not going to muck up things with that. So if I know the hydroxide concentration, I can now use that to find the pOH. So my pOH is the negative log of 5.6 times 10 to the negative third. It is 2.25. So now my pH is equal to pKw, which is 14, minus 2.25. So my pH is 11.75. And that seems like a reasonable answer because we said the carbonate ion is a base and we'd expect it to be a basic pH. Sure. Okay. So I had my two equilibria. My carbonate plus water is in equilibrium with hydrogen carbonate plus hydroxide, and then my hydrogen carbonate plus water is in equilibrium with my carbonic acid plus hydroxide. And my first ice chart, I had 0.15 molar, ignore water, 0 and 0. Minus x, x, and x, 0.15 minus x, x, and x. And my Ka1 for this, going back a couple pages where we figured these out for carbonate, or my Kb1, I mean. Kb1 was 2.1 times 10 to the negative fourth. Over here, I set up my ice chart. My hydrogen carbonate starts at x. My carbonic acid is 0 and my hydroxide is x. So now I have minus y, plus y, and y. At equilibrium, x minus y, y, and x plus y. And my Kb2 here was equal to 2.2 times 10 to the negative eighth. This is very small. And since Kb is very small, we can ignore y compared to x. So if I ignore y compared to x for the final hydroxide concentration, it's x, which I calculated right here. So I didn't need to recalculate it again because I already had determined my hydroxide within sig figs from the first ionization. Okay, so that's why.